All right, so let's see. So, okay, max 29K IAPS. Okay. So yeah, um, once I've got some of this Quincy stuff more taken care of, I can maybe try to take a look and help debug what's going on there. It is interesting that you saw it with a second NVMe drive as well. Um, who knows, maybe Master is messed up or something, but I'll see if I can take a look. All right. So the what Gabby's talking about is he's had trouble on one of our fast NVMe test nodes internally with Master for the last couple of weeks, getting good test results out of it. In the past, we've seen around 70 to 80,000 small random write IOPS, and he's seeing more like 20 to 30 right now. I've tested something fairly recently that I thought was based on Master on the Mako nodes and still saw high performance. But I should go back and just verify that that was actually on Master. I think it was. Um, but anyway, things to figure out and look at. Okay, so this week I didn't get quite through all of the old PRs, but I don't think there's probably been a ton of updates on them, so I'm not going to worry about it too much. We do have two new PRs that I made this week, and these both relate to the AV allocator topic that we've been discussing. So a reminder, we changed the way that we determine when to go into best fit mode in the AVL allocator instead of continuing on in near fit mode last summer. The changes that we made basically limit based on the number of bytes distance we have to search and also the number of iterations that we search. So the test result data that I've got, there's a whole bunch of it now, is here. And the gist of it basically right now is that even trying to, sorry, you should look at the AVL adaptive NF tab. So the gist of it right now is that we're seeing that on these Samsung drives, whenever we kind of use these limitations, we see kind of a fairly big slowdown in large sequential writes. It appears to be because the allocation pattern changes dramatically. Instead of doing really linear allocations, just straight across the drive like we did previously, now we're seeing this kind of flurry of IOs spread across the disk. All 64K, we're not fragmenting smaller than that. We're really consistently writing 64K IOs, but this kind of pattern of spraying the entire block device with IOs makes these Samsung drives unhappy. So I did try increasing the parameters that we'll have in that PR, kind of 4x and 8x. Those are on lines 8 and 14 in that first Mako kind of set of columns. And that helps, but it doesn't eliminate the issue. So it turns out that it's really hard to tune that. It's really hard to know, well, how many bytes do you let it search? How many cycles do you let it go through looking for things or looking for space? So I wrote this other PR that's in the Etherpad here that makes it so that instead of deciding when to switch into best fit mode based on the cycles and bytes, instead it just does it based on the amount of time that you've spent in near fit mode. And when you exceed that time, then it switches. The default I've got right now is 1 millisecond. That was enough to kind of keep the behavior in the fast mode. So that seemed to work. It kind of makes the behavior more like it is in Quincy, or sorry, in Pacific, at least up to 16.2.7, and makes the Samsung drives happy again. The downside is, it's new code, right? So yesterday at the CLT meeting, we kind of decided that we wanted to look at more tests, especially on hard drives, and see what the impact is there. David Galloway very kindly got one of the older Incerta nodes set up with CentOS Stream for me really quickly. And so I did start getting results from those. They have Intel P3700 NVMe drives, and they have hard drives. And so I looked at the P3700's bare, and I don't have results yet for my PR, but I do have results for Quincy with the kind of default current behavior and then kind of reverting back to the older Pacific behavior. And there, the effect is minimal. There seems to maybe be a slight effect because it's always a little slower with the Quincy defaults. It's not dramatic. It's maybe like 1%, but it does seem to be consistently a little slower in that mode. Whereas on the hard drive case, which is really interesting, in the tests that I run, these are really short. This was kind of like the minimal set of tests I could run to showcase the behavior on the Samsung drives. It looks almost identical. There's very, very little difference, but there hasn't been a lot of writes, like small random writes to the drive. And I can verify that I still see the same patterns that I see with on the NVMe drives, but it's a little different. In this case, we still see these 64K IOs, but they're lumped together in groups of 64. So in reality, we're writing like 64K writes completely sequentially in the case where it's like Pacific, the old behavior. And then in the current default Quincy behavior, we see 64K writes grouped into blocks of 64 that are written sequentially, and then those are scattered around the disk. And when I looked at longer running tests, where instead of running these tests for like 30 seconds, they're running for 30 minutes. In those tests, it actually looks like this change was maybe slightly better. When I disabled it, I saw lower numbers in some of the tests, at least initially. By the third iteration, maybe less so, but definitely it was different. So it's possible that actually the current behavior in Quincy is doing better on hard drives. Maybe. Hard to say. So that's where I'm at right now. Need to do a lot more testing probably on this, but we do need to make a decision on what to do for Quincy. So really consistently, we've seen that this behavior on the Samsung drives is bad. It hates the change. Well, these drives hate the change that we made, and we're able to get into the mode pretty easily where they're showing fairly significant degraded performance. Whether or not on other NVMe drives and the Intel drives, there's very little difference. They don't seem to care one way or another. Now on hard drives, we'll have to see how this plays out. But yep, that's basically it. So one question, Igor, you and I have been discussing this quite a bit. I wanted to ask you, with the test that you've been running, that workload test, Do you have kind of any idea like what's happening in that test where you're kind of showing the current behavior, faster allocations than it makes sense. I agree with you that it would do that, but do you know what the workload is there?
Do you mean this allocation replay stuff?
Yeah, exactly.
Well, I think the the issue is not the payload itself, but the implementation of the disk or of the space. So the replay payload is pretty trivial. I'm trying to replicate the payload coming during DB compaction.
Okay.
That's just allocating of 500 kilobytes. So it allocates chunks uh, in 500 of 500 kilobytes, and using 64K allocation unit, while the user allocation unit is 16K. So it's a single volume, and DB shares the volume, and hence in high fragmented space, it might be tricky for BlueFS to get 64K continuous blocks. And it looks like without these limits on AVL allocator, might take pretty long time to search for such continuous blocks.
Yeah. I'm surprised that AVL allocator is taking. I mean, it sounded like you were seeing even in the real case like 70 to 100 milliseconds for.
Right. So I definitely have seen the log for DB compaction, which exposes like 70 milliseconds delay. And I thought that I saw pretty the same with replay stuff, but at this point I'm not sure about that, since I could miss this nanosecond versus microsecond stuff.
Yeah. I'm not super concerned if it's like microseconds, right? I mean, it's still a little concerning, but it's not like crazy. But if it's in the field we see like 70 milliseconds, that's really bad.
Well, again, it's not exactly regular operation. It was compaction. And the compaction, well, for regular operation, I can share just latency graphs before with default hybrid allocator, and then after switching to stupid one. And the difference is crazy.
Yeah.
And on the same cluster, I performed DB compaction, and for hybrid allocator, it took something like 50 minutes versus 5 minutes on stupid allocator.
Yeah. And that's really crazy, right?
Right. So, but what compaction requires from the allocator is the repetitive allocation of these 500K chunks of 64K continuous blocks. So it's probably the worst pattern in case of fragmented space. So
Yeah.
every allocation should needs to look up for, well, this continuous block, which is a tricky scenario. But again, the regular operation was crazy as well. And actually, I think that if I compare allocation durations for stupid and hybrid allocator, so I can see something like 2 microseconds versus 1 or 2 milliseconds. So probably that's not, so that's actually great difference as well. So it might cause, well, pretty significant impact on the overall performance, because while Avail allocator searches for this continuous block for 2 milliseconds, it's locked, so other operations are not able to proceed on the same or again allocation. So in fact, with 2 millisecond allocation duration, you can get something like 500 allocations per second.
And is it, or is it always working in 64K chunks?
You mean BlueFS?
Yeah. So like when we talk to the allocator, we're never requesting larger than that, or like for a 4 megabyte write, will we request a contiguous space?
BlueFS can request larger chunks, but the allocation unit it requires, so minimum allocation size is 64K.
Yeah.
So every, as I said, I'm trying to, in my replace scenario, I'm trying to allocate 500K chunks, but the allocation unit is 64K. So it can return single continuous block of 500K or a bunch of blocks no smaller than 64K.
Yeah. So,
but the space itself is fragmented using 16K blocks. So if you have pretty fragmented space, again, it might be tricky to find continuous blocks. That's the key point here.
yeah. But the reason I was asking is like when you're seeing some of these big numbers come back, that's for a 512K allocation?
Well, that's the size which compaction tried to allocate, and that's the size I was originally played with.
Okay, so that's what that nanosecond number in your output represents.
Right, but well, probably for when I shared the results, I was using 128K block. It's present there, so the sizes are present there. So maybe I forgot the original number when shared these results to you. So yeah, as far as I remember, these shared results contain 128K. And yesterday I did a brief check again with 500K blocks. I'll sort things out and share that a bit later, but again, the difference between stupid allocator, default, well, this new patched hybrid allocator, and original ban, so the original behavior is much worse than stupid one or this patched hybrid allocator. I mean patch which introduces these search limits, not your rollback patch.
Yeah.
So you can see, you can see this duration, then want unit max hint in hex. So the first number is the requested block size, then allocation unit, and well, some additional parameters. So it was 128K chunks.
Okay. Okay. So in this case, we could either get a 128K contiguous chunk back or two, or would be or 264K, or were you saying 16K?
Right. Yeah. It would be then allocation unit is 64K. So you can
Okay.
the result would be one chunk or two chunks.
Okay. And in my case, the test I'm doing, since I'm doing a 4 megabyte write, presumably we're asking for 4 megabytes from the allocator, and it could give us that back in 64K chunks. As I see, also.
In your case, it might get even 4K chunks. So since we now have 4K allocation unit for
Okay,
both SSDs and HDD, so potentially you can have up to, well, down to 4K blocks.
sure. So we could do up to, in that case, 1024 um, uh, uh, individual uh, blocks back from the allocator.
Yep.
I don't think we are, because it looks like I'm always writing out in units of 64K.
Yeah. Well, as far as I understand, the hybrid allocator tries to provide more or less continuous chunks, so it's a completely degraded state when it will return 4K chunks.
Any idea why we're doing writes as 64K writes to disk? Like where that would be happening?
Well, I recall we had some stuff for spinners to match our original behavior with 64K chunks. Not sure if that somehow affects SSDs as well. So I was thinking it was introduced for spinners only, but maybe it somehow affects SSDs as well, or maybe something else is taken into account.
Sure. Well, the fact that you see this, huge difference, right, when you switch from basically, I think basically what it means is we're only spending a very small amount of time in best fit and near fit, and then switching to best fit right away. I mean, almost to the point where I wonder how often we're even using near fit in these tests that you used.
Well, I think that since this dump was on a highly fragmented space, it could use, well, that second mode. I name it all the time.
In my test, it's looking like we're really quickly going into best fit as well, almost to the point where I wonder if you'd be better off just not even bothering doing near fit search at all.
That's weird, to be honest. Because as far as I remember, there are some tunings in the allocator which enforce switching to that second mode in case of pretty high full ratio, like 90% of the disk is full.
Yeah. Well,
switch to another mode.
Well, it's Kefu's change, right? The one that's
Well, I believe he borrowed that from EFS or something like that. So the ideal allocator came from that stuff. It wasn't written from scratch.
Oh, okay. That's their space map implementation.
All right. So if you find the original PR introducing ideal allocator, or even in this PR which bring these limitations, they mention the FS or something like that.
Okay. I wonder if our behavior is just a lot different somehow. Because it really seems like we're just very, very easily going into best fit. And it doesn't bother a lot of the hardware. Like the Intel NVMe's don't seem to care at all. But
Uh, but so you are saying that the full ratio for disk in your case is pretty low.
exactly, it's very low. It's like 3%.
Range. So we need to revise this logic for mode switching and maybe something from there, or I missed something.
It makes me wonder if the search, if like the near fit search isn't doing the right thing. It could be like somehow searching in the wrong way or something, and then we just revert to best fit.
Just got an idea, Mark. If you are able to get the disk into this bad state when allocator behaves improperly, could you please dump this allocator state, and we can investigate it locally with replace stuff and things like that. Not to mention we can troubleshoot hybrid or other allocator and check why it's switching to a different mode.
Yeah. So I mean, in terms of the performance problem, I actually recorded the block trace data so that I could then play back the same workload using FIO and ignoring timestamps and that kind of thing. And if I just replay back that write workload on the drive in isolation, it does it fine. It seems to require the lead up to get the drive into the state that it's in.
Yeah, but I'm talking a bit about a bit different stuff. So once your USD is in that state, you can use admin command, something like Ceph USD, Blue Store. I can share the exact command. So it will dump the allocator state in JSON format to the disk. So I can take it and replay with my tool.
Okay.
And then apply some custom allocations to it, and maybe insert some additional login in the allocator and investigate what's happening, why it switches to different mode.
Sure. And it doesn't require the Samsung drives. Like I see the same pattern on everything. So it's not like this. It's just the Samsung drives are slow. It's not that there's yeah. So we should be able to replay it anywhere, pretty much, or do this anywhere. Yeah.
Well, for replay, I don't need drive at all. So I just so the replay tool just tries to allocate to call allocator, and then measures how long does it take and what are the results. Well, at least we can extend that. So it doesn't no need for specific devices for that. Everything happens in memory.
since I've got this window shared for people, I'll show what these patterns look like. So this is basically what we're seeing with the current defaults. Uh, this looks a little different depending on the drive that you're running on because some are faster than others. So it might show slightly different oscillation behavior. But this is kind of what we're seeing in master right now. And this is this kind of behavior where it's just going straight linear allocations across the disk when we have uh, basically the defaults tuned to what they were, or what they the equivalent of what they were back in Pacific. And this kind of behavior, the Intel NVMe drives don't care about. They're totally fine with it. They don't. They more or less are the same performance, whereas the Samsung drives seem to want this kind of behavior that we had previously. And actually, I'll change to the other PR. Let's see. This is again Quincy default. Oh, sorry, Quincy off. This is the old behavior. Um, this is the new behavior. This is with tuning it to use more, to basically do a bigger search. And we still see this. It's actually doing a little bit better though. Same thing with even bigger search space, 8 times what the default is, still seeing this pattern. And then this is the change I made to do it based on time with a small, well, sort of small, 500 microsecond search time allowance. And then when we move up to 1 millisecond, that's when we go back to this behavior where we're in near fit instead of falling back to best fit. We see this linear allocation and high throughput on the Samsung drive. And I did 2 milliseconds as well, but it's the same behavior. So yeah, Igor, what perplexes me is that on a workload like this with a very, very lightly filled disk, we could have near fit take a millisecond, right? I mean, doesn't that seem crazy?
Does.
That's why,
So
yeah,
millisecond to get to allocate 4 megabyte chunk.
yeah,
What are you asking?
yeah. So that'd be a 4 megabyte chunk. Um, hey, Casey mentioned he's got to go soon. Igor, would you have time to continue this offline? Maybe we can talk more about it.
Uh, Maybe not exactly after the meeting, but in 30 minutes after that.
Okay, cool. Maybe we can continue this. We're really in the weeds here. I don't know if people care about this that much or not, but maybe we can wrap this one up for now for here. So Casey, the tracer PR, did you have anything quickly you wanted to mention about it?
Well, there were some new results since last week comparing performance when it's disabled, and it looks like there was no overhead at all, which is really promising.
Cool.
I think that Omri, initially he was running the test for like 30 seconds. So what he really observed was whatever was happening at the beginning, and it was really fluctuating. So now he's running that for 2 minutes or 3 minutes, and it is much more stable.
Okay. Well, that sounds hopeful. Casey, we're not merging this for Quincy though, right?
That's correct.
Okay. So honestly, I probably won't look at it until this is all done. We're trying
Yeah,
to
that's fair.
desperately. Yeah.
If anybody has suggestions for other ways to evaluate the performance of this stuff, please follow up on the PR.
Cool.
Yuval, did you have anything else to add?
No, just that it looks, I mean, there's still quite a bit of work to do when tracing is enabled, but this is a different story because by default it's going to be disabled.
Yeah. Yeah. And if it's really like, zero overhead or like 1% overhead, it's not a big deal. We can eat it.
Thanks.
Cool.
Thanks, Mark. Sorry to interrupt.
Oh, no. We, Igor and I were going on about allocators. We could probably spend the next 20 minutes continuing to discuss them. Duty. So, yeah. Maybe moving on. Gabby, we were talking in core about the performance issues you're seeing on Officinalis. Yeah, I don't know if that's master that's slow. I don't think it is, but it could be. Maybe that's. Have you tried testing Pacific out of curiosity?
No, I did not. I only use master.
So we know that definitely like Pacific 16.2.7 is good. I wonder if maybe if would you possibly be able to repeat your test with that and see?
Sure. If you could send me what's the SHA for Pacific. I don't know what's.
There's a tag for V16.2.7.
Yeah, if you could just send me just a tag.
Yeah, that should do it. I just linked it or put it in chat there. But here I can give you a link to it too. Okay. There you go. So yeah, just check that out, and it'd be really interesting to see if that fixes it or not. If it doesn't, then yeah, we definitely need to figure out why that node is going slow now.
Could you take maybe a look in my machine and see if there's anything fishy?
Here, yeah, I can probably at least just take a quick look. You're on 09, right?
Yes. So when I try to change from to NVMe 1, the thing just stale. So I'm using OSD device 0, which is mapped to NVMe 1.
Yeah, and you said that switching to other ones didn't help, right?
I try switching to OSD device 1 on all the settings. So I got this one x1 BS file. I try changing all the setting. There is the OSD data device and Blue Store and so on. So I try to change all of them from from 0 to 1, and this thing just didn't work.
Okay. I see that the test run I did also showed low IOPS. Go and take a look at it. IO depth, good. Interesting. There appears to be writes in this test that I did. I got this. I was on it earlier with you, and it appears that there are writes both to NVMe 0 and NVMe 1 in that test at the same time. I wonder if journal was, or the Debian wall was on one of the drives, and
So
the block.
everything is on the same drive, right? In this test.
The one I'm looking at right now, it was split. There were writes going to NVMe 0 during the test, and there were writes going to NVMe 1 during the test. Unless there's something else writing to NVMe 0, but
So block DB and write ahead. Actually, I take it back. The DB and write ahead log, they are on 0, but the block is on 1. So actually, there is no problem.
yeah, it should be fine. It was just an interesting thing that it was split. The processes using 4 and 5 cores and 7 gigs of memory in this test. Okay, Gabby, my thought is maybe we take this out of the performance meeting, and I think we wall clock profile the OSD while it's running and take a look and find out what it's doing. Let's start our own chat after the meeting here, and then we'll
So
see if we can make
just
this work.
ping me and I join.
Okay, sounds good. All right. Anything else that anyone wants to bring up this week before we wrap up? All right. Well, then, thank you everyone for coming. It may have been a little dry this week. Sorry about that, but thanks for attending, and we'll see everybody next week.
Yeah, and Mark, I'll ping you in 30, 40 minutes when I'm
Oh, okay. Sounds good, Igor. Thank you. Bye, guys.
Bye.